Okay, so give us 1 minute. We are trying to make the coin co-chairs delegate so that they can actually run the meeting later. Okay. Eve, Marie-José, and Jeffrey, I think if you would kind of log out and log in again, you should have delegate privileges like Lisha has, and then that could make you could allow you to control the session.
I'll try.
Thanks.
I'll give that a shot.
So it didn't work. Let's wait for Marie-José. No luck. Okay. Then we figure out another way.
Okay.
Okay, let's start. Welcome everybody to this IETF 114 joint IRTF session on ICN and computing in the network. So this is a joint meeting of Icnrg and Icnrg. So we have some common topics, some mind share in like distributed computing and networking. So we thought it'd be a good idea to try a joint session. And so that's what we're doing today. So today, the first session will be on ICN topics and the second half will be on coin topics. I'm the co-chair. My other remote co-chair is Dave Oran. And we have Lisha Zhang in the room who kindly agreed to help us as a local co-chair today. Thanks a lot. Yeah, as all meetings, this one is recorded. So just a few housekeeping announcements. First of all, if you are in the room, please make sure you're wearing an N95 or at least FFP2 mask. Also, we are, as all other sessions, are using the Meet Echo queue management. So please sign in to the session using the Meet Echo client or Lite client, and make sure you have your audio and video off. And I think remote participants by now probably know how to use their headsets and microphones. So please do that. And okay, let's skip this. So we are following the IETF IPR disclosure rules. So in essence, that means you are expected to let us know if you hear, see, or say anything that has IPR relevance in a short time frame. Okay, this is obviously recorded, and there's also a privacy and code of conduct. Please consult these links if you are not familiar with these rules. And finally, yeah, we like to remind you that well, we are here to do research, although that we are using the same mechanisms for managing documents, and some research groups are also publishing RCs. We are typically we're not doing standards, so this is purely for research, for enabling experimentation, and so if you're unfamiliar with this, check out RC 7418. Okay, so this is Icnrg. Please join our mailing list if you haven't done so. So we earlier agreed on having Marie-José as a note taker for the first half and me for the second half. So that's all sorted. And this is the ICN agenda for today. So we're going to hear about the update on ping and trace route and the update on the data time encoding spec. And then Nikos is going to present research work on selective content disclosure using zero knowledge proofs. And yeah, that's it for now. And let's start with the ping and trace route update, unless there's anything else you want to suggest for discussion today. All right. So I'll stop sharing. Dave, I can just bring up the slides if you want. So Dave, can you hear us? So he may be experiencing some connectivity or audio issues. Let's give him a few more seconds.
Okay, can you hear me?
Yeah.
Yeah.
You can.
Oh, finally, okay. So this will be really quick. Let's see, I think I can drive the slides, right? How do I drive the slides? Just a second. Need to take control of the slides.
Maybe you should just start sharing yourself and then you can control them.
All right, I can do it. Just a second. I had to share it myself.
Okay.
There we go. Now I think I can drive them, right? Huh. How do you drive them? I've done this before. I've got the slides shared.
So I can't control them. So.
Here it is. Never mind.
Left and right arrow.
Okay, here we go. Okay, so these two specs have been around for quite a while. They've been advancing slowly. We got them through research group last call a few months ago. They went into IRSG review. Colin did a pre-review, and Chris Wood did the IRSG review, so thanks to both of them. And during the review cycle, we actually got the attention of some folks who hadn't participated earlier. Thank you very much. And Jun Chao offered us some comments at the same time we went through the IRSG review, and we've gotten a few more since then, mostly relating to some technical problems with how we decided to do the field encoding in NDN packets, since the spec supports both CCNX and NDN as underlying protocols. So the latest versions are the ones that were in review. So we've made one set of updates. Colin seems to think his comments were addressed during his initial review through the IRSG. I already mentioned Jun Chao's comments about NDN packet format. And we got some really good sort of general comments from Chris. And those have been responded to on the list. And we'll try to get those changes into the spec pretty quickly. So there's one other area where we seem to have blown it on the packet encoding for NDN, which is how the path steering capability, which is not actually in that spec, it's in another spec, gets placed in the ping and trace route packets. So we need to do a little bit of technical work there, both on the ping and trace route specs to point to the path steering spec. And then since the path steering spec is mine, I'm going to do an update of that to get the NDN packet coding correct. So moving forward, we're going to update both of those drafts plus the path steering draft in the next few weeks. And hopefully that will be able to move everything forward. I'll make one quick note that the path steering draft is still an individual draft, and Dirk's going to talk probably at the end about whether we are ready to adopt that as an RG item so that we can move it forward in parallel. The ping and path steering, the ping and trace route can go forward without path steering since it's useful in the absence of that. But they work, I hate to use the word synergistically, but that's probably the right word, together. So having them all in the game here is probably a good idea. So I'll take any questions folks have. This is pretty straightforward. Going once, going twice. Okay, anything you come up with, please either contact Spiros and me directly or post on the list. Preferably post on the list. So thanks.
Thanks, Dave. So actually, since you mentioned path steering, I actually jumped ahead a bit too fast. Let's just quickly look at our documents. And so here's a list of our current active documents. So we just heard about ping and trace route. We are going to hear about the delta time encoding in a bit. We have the LTE 4G draft that I think is about to be published. And we have CCN info, which also has been around in IRSG reviews and so and for some time. So Colin, if you're listening, do you know what's the latest state of this?
The CCN info draft. Give me 1 second. Sorry, I'm trying to listen to too many meetings at once.
Yeah, sure.
As far as I know, we're still waiting for. Last I checked, we're still waiting for responses to the ballot. I think it's got 2 yeses, but I think one of them is you, and you're the chair, so you would have to recuse. So I think it doesn't quite have enough position. So I think if I'm remembering right, I need to remind the IRSG and see if we can persuade someone to either change their no objection to a yes or someone else to review it.
Okay. Yeah. Okay. Thanks.
I don't think there's any great problem here. We just need to finish off the reviews. Although I think there were some comments on the list. Did they get reflected yet?
I think, yeah, they have been reflected. I think this should be ready to go, to be honest. I think probably good to remind people once and get this.
Yeah, I will remind people again after this meeting. I've sent a couple of reminders already, but I will do it
Yeah,
again.
I know. Okay, great, thanks. And yeah, so Dave just mentioned path steering, which is yeah, not kind of really required for ping and trace mode, but it's like in the same mental model of using ICN. And just to remind everyone that there has been an IPR declaration on path steering. So just to, I think we shared this on the mailing list as well, but just for completeness. And last time we discussed adopting it as a research group document. We didn't really follow up on that so far. Just checking if there are any opinions on that. Okay, so then it's up to us to follow up on the mailing list. So yeah, maybe to say if you could note this on the meeting notes, that would be great.
Let me just mention what's the deal with this IPR declaration. So this is Cisco IPR, and Cisco, of course, has the standard IETF, MAD type IPR disclosure, which says you can use it just fine, no royalties, anything like that, for IETF documents. Now, the problem is that Cisco has no policy for IRTF documents since they're not destined to be standards. So Cisco did not put in an IPR declaration on path steering because they didn't know what to say. So this is the third-party declaration by me. So just so people understand, this is in this sort of nether world where Cisco doesn't know what to say about it, since they don't have a policy for non-standards documents.
Yeah, thanks. That's good to know. Okay, so with that, let's move on. And so next on the agenda would be Thomas, who I think is in the room, and I think I should bring up the slides, right?
Yes, I'm in the room, and it would be nice if you drove my slides. So yes. This is an update of the alternative delta time encoding for CCNX using compact time formats. This was recently adopted, or after last IETF, or sometime then, as a research group document. So this is actually the research group document version 0 I'm presenting, which has addressed a couple, let's say, cosmetic things and also editorial aspects. So I will give a brief recap. Next slide, please. So what is the objective? We are looking at constrained IoT networks here, and in this context, the research group has produced the RFC 9139, which is ICN low pan, and there was one open question on how can we make the time encoding more efficient, because in these constrained environments, the bandwidth is low and the latency is high. We have slow links, lossy links, so the more data you put on the link, the more you lose. And this the I mean, generally the field of power is that the node processing capacities are larger and less battery energy consuming than using the links. So we want to pre-process or process on the nodes to save link bandwidth. Next slide, please. And for this, we look at the TLVs that represent time. So this is the way it is encoded currently in the CCNX specs. So we have relative times that is that is an offset with given in milliseconds with a variable length. So it can be larger than 1 byte. So there's a length field, and then you can have a corresponding longer time value, and then there are absolute times that always have a length of 8, and this is a UTC time encoding, an epoch time encoding in the length of 8 bytes. So next slide, please. So the mechanism we want to introduce here is a compact time encoding that supports a dynamic range and is built in milliseconds from an exponent in mantissa, so that you have have a relatively high precision in the small time values and a relatively coarse-grained precision in the larger values. So if you look at the formula, you have the subnormal part where you actually start with the distinction between the two formulas is that the upper formula starts with a 0. So you have basically you divide the mantissa, and then you divide further for the value of an exponent value of 0. If the exponent value is larger, then you actually go into an exponential representation, which is coarse-grained in larger values. So next slide, please. So the existing time values are in interest and data messages. So in the interest lifetime, you have a relative time in the hop-by-hop header, and in the interest message itself has a signature time, which is an absolute value. And for the data, you have an absolute value for the hop-by-hop header, which is a recommended cache time, and you have once again a signature time, which is also an absolute value. So the idea is to convert the recommended cache time to relative times and to compress interest lifetime, but leave the signature times intact. So next slide, please. So what changes is in the case if you're given the currently existing protocol, in the case where it is encoded a length of 1, so that means a short length field, then we want to put in the compact time offset, and in the case the length value is larger than 1, in the encoding we use the regular. We just keep the regular timing intact to make the protocol to plug into the existing protocol encoding, because as we understand, not all CCNX packets are on constrained devices. So next slide, please. So this is the case for the protocol integration for the recommended cache time. Before it was an absolute value of length 8. Now we change to this duality. If it's encoded with a length 1, then we use a compact time offset of 1 byte. If it continues to be length 8, then it's the regular timing value. So next slide, please. Sorry, we already have the cache time. Sorry, yeah, I'm fine. I was confused. So what are the diffs to the version 0.5 of the individual draft? So we updated the integration with the interest lifetime and the recommended cache time to interpret the corresponding values. We added equations to approximate the conversion and to estimate the error that actually occurs, because you cannot represent every value anymore. There's an approximation formula which helps to see what error you're producing. It's a simple formula. We also rearrange the references and the acknowledgement section. And from our side, this is a pretty mature document, but please feel free, feedback to get this document finalized. Okay, questions?
Rick Taylor, Ori Industries. Just a sort of general question on this one. How far does this deviate from IEEE 754 formatting? I notice you've got no sign bit. I'm assuming you don't support infinite values.
No, it is. I've actually we had this discussion. I mean, there are different time formats existing. There's this IEEE format. There's also a time format by the IETF that was introduced, I guess, in the context of some routing protocols.
So my question is not about the time format, it's about the floating point format. So everyone's pretty well experienced with IEEE 754 floating point for 32-bit floats and 64-bit floats with silicon support. I know there's an 8-bit float support used in graphics quite heavily.
Yeah.
If this deviates too far away from that, are we losing the ability to use silicon that already understands how to do this work? I know I'm just interested in the diff. I know you don't need negative times.
No.
And I know you don't need unrepresentable times, you know, division by 0, infinity, and so on. I'm just wondering whether the working group has considered the benefits of not including support for those weighed against supporting something that's pretty industry standard from a sort of silicon perspective as a sort of well-known way of dealing with floating point numbers.
I mean, we had the discussion. We had a longer discussion about the actual format, and also we were also discussing the IEEE format. I'm not sure I recall everything correctly in the moment. So maybe, I mean, if this is, should probably have a follow-up on the list. If we need to recap all this discussions. It's actually something like 2 years ago or so.
It's great work. Don't get me wrong. I just think there's some nuance in here, but thanks.
All right. See nobody else in the queue at the moment. Yeah, thanks a lot, Thomas and Cenk and team for progressing this, and also for everyone paying attention to details and providing comments. So we hope to get this finished in the near future. Okay, so let's move to our next agenda item, and this would be Nikos with his presentation, and he wanted to run the slides himself. Yep.
Can you hear me?
We can. Access granted.
Okay. So I'm sharing my screen now, and I don't see the conference tool. So if there is a comment or somebody want to intervene, please.
I'll let you know.
Yeah, let me know. So I'm going to present to you our ongoing work on selective content disclosure using zero-knowledge proofs. I'm Nikos Fotiou from the Athens University of Economic and Business, and also in this meeting is George Xilomenos, who is part of the team doing this stuff. So a bit of a background related to this talk. The main building block of the solution that I'm going to present is a digital signature scheme called BBS, which was initially proposed by Bonnet and others in the paper included in the first bullet of this list. And this signature scheme was initially designed to allow users to sign group of messages. Then many others extend this scheme to include zero-knowledge proofs. And one of the latest and most important extension to this scheme is by Kamenskis and all, and you can find it in the paper included in the second bullet of this list. So earlier this week in this IETF meeting, there was a talk by Tobias Luker about this signature scheme. Tobias and others are using this signature scheme, and they are developing a solution in the context of identity foundation that applies this signature in a technology called verifiable credentials. And using this technology, they allow users to selectively disclose claims about themselves, and all these claims are included in this so-called verifiable credential. So the purpose of the talk of Tobias in this meeting was to propose the adoption of this signature scheme by IETF, and in particular by CFRG. And if this happens, it's going to be very exciting. So many related works are investigating this signature scheme, mostly in the context of digital credentials. What we are doing in our lab is we are trying to apply this signature scheme for implementing selective disclosure of content. So currently, we are running two projects. The first one is called Second, and it is funded by NGA Atlantic. This is in cooperation with the University of Memphis, and in this project, we are exploring the application of this signature scheme in NDN. And as a matter of fact, we have scheduled some experiments to take place in the NDN testbed. The second project is called Select Share. It is funded by NGA DAPSI, and there, with two SMEs, we are applying the signature scheme for providing a solution that allows secure sharing of IoT measurement data. So you can find more information about this project, as well as reports, pointers to source code in the URL included at the bottom left part of these slides. So what is our goal with these projects? We want to develop a solution that will allow caching of data on which we can make computations. So we are not talking about bulk data, but we are talking about data like relational database or data streams generated by IoT devices. This data can even be the log of operations in a distributed ledger, or it can be the graph of a distributed social networks, you name them. So the applications are countless. So we want to allow the storage of this data in third-party storage providers. We want to allow users to request portions of this data. And at the same time, we want to enable these storage providers to provide proofs of integrity, but without sharing with them signature keys. So let me give you an example. So this JSON object represents a data item that includes information about some measurements generated by an IoT device. And this file has been assigned by somebody, for example, the device owner. And this file is stored as a whole in a storage node, which can be something akin to a web server, to a CDN node, or even to a cache. And we want to enable users to perform queries like this ones. So I want from this particular file to access the temperature measurement generated by this particular device. And the reasons for making such queries are either this user is interested only in these two fields included in this file, or even more importantly, this user is authorized to access only these two fields. And we are working on a solution that allows firstly users to perform such queries, and we do that in a way which is compatible with NDN API. Secondly, we allow storage nodes to respond to these queries in a way that allows users to verify the integrity and the correctness of the generated response. So I will first introduce the signature scheme, which is the main building block of our system. So I guess you are all familiar with digital signatures. Traditional digital signatures allow a signer to sign a message, and then a verifier can validate the digital signature of this message using the public key of the signer. So group signatures are very similar. The only difference is that the signer, instead of signing a single message, it is capable of signing a group of messages. And then the verifier can, in a similar way, validate the digital signature of this group of messages. So far, there are no significant difference, but group signatures have a very nice property. They allow a third party, which we call the prover, that has access only to this group of messages and to the digital signature, to hide some elements of this group of messages, and at the same time provide a proof that proves that the revealed items are correct. So more formally, this proof is a zero-knowledge proof that proves that the prover knows a digital signature that covers both the revealed and the hidden messages. And since this digital signature can only be generated by the signer, this zero-knowledge proof is a proof that the revealed messages have not been modified. So works in this area are focused on two problems. The first problem is related on how to transfer structured data in something that resembles to this group of messages, so that the BBS signature scheme can be applied. So in our work, we focus on data items encoded as JSON objects, and we are using a mechanism called canonicalization. And this mechanism transports a JSON object into an array of messages. So you can see in this example how this JSON object on the left has been flattened to this list of messages on the right. So this is a very simple and straightforward example, but for more, let's say, advanced JSON objects, like those that includes arrays, the canonicalization approach is not straightforward. And we are using a canonicalization algorithm that we have created by ourselves, and it's the security properties of this algorithm have been formally verified, and they are included in the publication that is located on the bottom of this slide. But there are also other working groups working in similar canonicalization algorithms, so there is a great space for research in this area. So the second problem is related how do we request specific properties of a data object. So how do we ask from a storage node to give us to generate a new item that includes specific properties? And in our work, we are using an approach called framing. So a frame is just a JSON object that includes the keys in which we are interested. So in this example frame, we indicate that we want to extract from a stored item the device ID, the temperature, and the created key of the metadata field. So if we apply this frame to our example JSON object, we'll get a new JSON object which is the same as the original one if we extract the fields that are not included in the JSON frame. So we are working on a framing mechanism that allows us to make more advanced requests. So, for example, here we have a JSON object which includes an array called measurements, and this array includes key value pairs, and we can have a frame like this one. So this frame in essence says that from the measurements array we want to learn all values whose ID equals to temperature. So if we apply this frame to this array, we get something like that. So again, this is an open area with a lot of space for research. So let's see how do we apply all these mechanisms to NDN. So we have an entity, we call it the data owner, that generates this structure item. So in this example, this JSON object. And this data owner signs this item and stores in a storage node, which we call it the producer. Then the producer assigns an identifier for this item and advertises it in the NDN network. Then any user can send an interest message that includes the identifier of this advertised item. Moreover, this interest message in the application parameters field includes the JSON frame that we want to apply in this item. And by convention, the identifier included in the interest message is appended by the hash value of everything included in this app parameters field. So this interest will end up in the producer. The producer will extract the JSON frame. It will derive the new item. It will perform the canonicalization algorithm. It will calculate the zero knowledge proof, and then it will send the output as a data packet back to the consumer. Now, a very nice, interesting property of this approach is that the data packet that the producer will send back, it can be cached by an entity which may be as well oblivious about our zero knowledge proof mechanism. And since all consumers interested in the same portion of the data item will calculate the same JSON frame, they will send interests that include the same coded identifier. Therefore, the cache can respond with the cached item, and the consumers can verify the provided zero knowledge proof, just like if they have received this item directly from the producer. So caching here is not prevented. Some performance results. We have implemented and evaluated the scenario. In this scenario, we have a JSON object, which includes 100 fields. These fields represents measurements from IoT devices. And in this graph, we show the time required to generate a zero knowledge proof, as well as to verify a zero knowledge proof as a function to the number of the revealed items. So as it may observe, generating the zero knowledge proof, the time required to generate the zero knowledge proof is almost constant. It is not affected by the number of revealed items, whereas the more items we reveal, the less time we need to verify zero knowledge proof. But in any case, the time required for these operations is less than 8 milliseconds. And I have to say here that for these measurements, we are using an unoptimized Python implementation of the signature scheme in an Ubuntu machine with 2 cores and 4 GB of RAM. So it's an ordinary machine, and these times can be greatly improved. So far, we have seen that this approach has some nice security properties, and it has low computational overhead. But it turns out that it also has some nice properties when it comes to storage and to communication overhead. So we compare our solution against an alternative in which each measurement in this file is individually signed using EDDCA digital signature scheme. So we assume that if we assign each record of this file individually, we achieve the same security properties, which of course this is not the case. And we measure the computational and the storage overhead. Of course, it's straightforward that having 100 different digital signatures requires more storage space as opposed to having a single digital signature. But also when it comes to the communication overhead, the bandwidth required to transmit the EDDCA digital signatures, of course, is proportional to the number of the revealed items, since we reveal 1 digital signature per item. Whereas when it comes to zero-knowledge proof, this is the opposite. So the size of a zero-knowledge proof is 272 bytes plus 32 bytes for every revealed items. So the more items we're revealing, the less is the size of this zero-knowledge proof. So if we reveal 32 items or more, we need less bandwidth for the zero-knowledge proof compared to an EDDCA digital signature. Of course, in both cases, the computational overhead required for transmitting these digital signatures is small. But in any case, this may be important in some use cases. So how can we move forward? This approach is using a new key type. This key is required by the BBS signature algorithm, and moreover, it defines 2 new signature types. One generated by the data owner, and the other is the zero-knowledge proof generated by the prover. So we can research how these encodings can be integrated into ADN or in other related architectures. As I told you, data framing and canonicalization is still an open problem where many things can be done, especially if we consider non-JSON encoded objects. And this also, many similar activities are taking place in other working groups, not only in IETF, but also in bodies such as Identity Foundation and W3C. So there are great opportunities for collaboration there. And of course, the sky is the limit when it comes to use cases for this signature scheme. And for example, I can imagine this scheme being integrated into routing protocols where routers advertise only a portion of the network graph, but many applications can be imagined, especially in the context of the Icnrg. So that's all. So as I told you, we are working actively in this area. Please contact us if you want to learn more information. We can provide source code and many other helpful pointers. So thank you.
Thank you very much, Nikos. Are there any questions for Nikos? So do you have a paper published on this already?
Not yet published. We have under submission.
Okay, great, thanks. So I was wondering about this JSON object integration, what you call framing. Is this actually a CRDT like operation? So like an addition this commutative and so so basically it doesn't really matter which order you do these additions. You can add or combine several objects in a row.
Actually, this is an open issue, so
Okay.
it is mostly no, it is only a read operation. Okay, so but suppose that you want to access an object and your response is cast somewhere. And then somebody else wants to access a subset of the object that you requested. So it is a very nice problem if this intermediate that has cast the previous response, how to generate a new object that can satisfy this the new request, which in essence request a smaller portion of the original message. And of course, combining such responses and creating new objects is also another very interesting open topic.
Yeah, I think so too. Great. Yeah, thanks for bringing this work to us. I think it fits really nice into the spirit of this session. So ICN and Icnrg. I see no other questions. Yeah, well, I think let's follow up on the mailing list if people have questions, and looking forward to the paper.
Thank you.
Thanks, Nikos. So just quickly, I realized that some people seem to be having connectivity issues or audio-video issues, which cannot explain directly. So it works perfectly for me, but could be a good idea to just share some of your experience in the chat. So just to maybe figure out what this is. So I'm connecting from Germany. I don't have any issues today, but I heard from others that it doesn't really work so well. Okay, let me just bring up our slides again. Okay, so just a few things that we shouldn't forget about. So we really wanted to get the Flick specification finished and published. So it looks like it's currently stalled again. So yeah, Dave and I have been trying to motivate authors and the group to kind of see how we can get this to last call. We think it's a really important specification. It should really be published. So yeah, if you have any idea how to move this forward, please let us know, or please also feel free to suggest text or anything if you think there's something missing, or and so on. And yeah, then of course we don't have that much time today, but so potentially there could be quite many interesting work items to discuss here. And here just a few examples that we came up with. So you're probably aware that there is a media over quick discussion in the IETF. So a BOF is this week. And so this is essentially a proposal to do something like, named data networking, you can say, over quick, or like an overlay network of quick relays, you can say. Of course, this could be done much better. Maybe that's an interesting topic for this community as well. I kicked off a discussion on self-learning auto configuration and also potentially NDN switch design on the main list. And so there is some interesting work that has happened in NDN CXX as a code base. I still think this could be optimized, and maybe that's an interesting topic if people are interested to discuss further. Then, we often, explain ICN as a good way to access arbitrary content in network, which is true. However, if you think about doing something equivalent like web protocols, so like HTTP3, for example, today, there are a few other things you have to care about. So things like name privacy, for example, maybe setting up something like TLS security context and so on, and maybe other things. So we think that that's actually an interesting topic and maybe something to work on. So we just saw an example for, say, ICN security work that kind of is connected to distributed computing and COIN. And we have talked about others before. So we would also encourage you to maybe, if you're working in this field, please share your ideas in this group. And I see Alicia in the queue.
You can hear me?
I think you have to move a bit closer to the microphone.
I look at your slides, searching for ideas for new work. I thought maybe a different way to ask the question is, what are the important problems that really need solutions, and start the look around in that direction. So like the current suggested list is give me an impression, sorry if I'm saying the bad words again, this is like you really look for work to do. On the other hand, research group really should addressing the burning challenges, not trying to figure out what to do next, but rather among all the problems, what are the important ones and still manageable to make progress. That's my 2 cents.
Yeah, point taken. Okay, I didn't explain this well enough, and of course, some of these points are actually motivated by actual problems. So, for example, like this first one, media over quick or ICN. I mean, there clearly is a problem in distributing real-time multimedia content over the internet, and so these media over quick ideas directly stem from this change in the CDN environment. And so you could say that this is the problem, and I see solution proposals right now that are, say, leave room for optimization.
So if I speak again, I think that if you look at the issue from that direction, that could give people much better ideas. If we just look at, say, media over ICN instead of quick, it wasn't clear, I suppose, to many people why you do that.
Yeah.
Given quick is really, they transport protocol that is catching all the attention.
Mm.
If you state the thing in a different way to something like media over quick does not address the following problems, and which could be addressed supposedly by over ICN, that will really get people moving to look into why there are issues with quick and how ICN can solve the problem. I would also take the floor now. I had some private exchanges. I guess you people remember with your chairs, also with Collins. I think ICN is a fundamental secret sauce. Is named and secured data. I am a bit afraid that the names are not really fully utilized as a semantic power. And the security seems to be, I don't know, ignored, forgotten, or otherwise people don't know how to do it, so they just skip it. I worry that without showing people how ICN can help address the security challenges facing the internet, we are really losing the real power of ICN.
Yeah. Thanks. No, I fully agree. So that, like, just quickly, this first item here is not intended as just like a protocol drop-in replacement or something. It's more likely referring to the bigger picture, the architectural problems. But we don't have time today to discuss this. So there's I think there's a lot to unwrap here, but we just wanted to inject a few ideas for maybe deeper discussions or actual work later in this group. But I agree about the security topic. That's definitely so. Also, when you think about web over ICN, of course, one of the really pressing issues. Okay, thanks. So we are done with the ICN part, but there's more to come on computing in the network. Yeah, we have this first bullet item for a couple of meetings now. We are really hoping things will clear up, but yeah, no promises at this point. Just quickly, please mark September 19th to 21st in your calendar. And this is where the ICN conference happens in Osaka, Japan, this year. Okay, thank you very much. Now let's just directly continue with Icnrg, and I would like to invite the Icnrg chairs to take over now.
Hello. Let's see. I guess because I'm not a delegate, I have to request. I have to request to share slides.
Yeah, probably. I mean, that's the best way. Yep.
Okay. Okay. It's so strange being on this side of the presentations. Okay. Hello, everybody. We're thrilled to have part of this session. I'm Eve Schuler, and my co-chairs are Jeffrey Hay and Marie-Josée Montpetit, and who are also here. But here is that we are all remote. Some of us had hoped to be there in person, and we're disappointed due to COVID and other airborne diseases that we are not there. We hope you all are staying safe. I don't believe we have to go through any of these slides because that was already stated at the outset of the Icnrg. But we have 3 very interesting presentations today. And we'll begin with Dirk, who will be talking to us about traffic steering at layer 3. Andy, who will discuss namespaces, security, and network addressing, and Tushar Swami, building adaptive networks with machine learning. And then we will discuss the need for an interim. There's several things that we've had on our to-do list for quite some time, namely a more pointed scoping discussion, really synthesizing many of the conversations, discussions, and debates we've been having on the mailing lists for many months, and really to take a step back and try to scope, as our charter states, rescope or scope more articulately or deliberately. And the other task that we would like to accomplish in an interim, possibly a separate interim, is to revisit the many drafts that have been written and how they fall into the architectural space. So with that, let's see, I think Marie-José wanted to, oh, well, you are here, so it's kind of funny, if you're not here, this is how you get to meet Echo. You won't get to see that. But nonetheless, because this is a shared meeting, it's a little funny how Meet Echo tracks or doesn't track the history of this. It will appear in the ICN meeting minutes and meeting under the data tracker, the meeting directory, but not in the Icnrg. So that, I think, is an oversight for Meet Echo, and hopefully we will submit that as something we'd like to see changed. Our minutes are being tracked in the same space as where ICN is, which is great. And thanks to all the people who've been contributing there. Marie-José, I think you had said you wanted to talk about our document status.
Oh, okay, yeah, I just wanted to say that we have 2 RG documents that we would like to move forward. One is expired, and the other one I think needs updates. We have a ton of other documents, and that as Eve said, there's a lot of them that maybe they're still good. Maybe some of them should not be. Maybe they just expired, and we don't want to continue anything. But it would be good for the authors to tell us what they intend to do. And again, I think this is going to be very much what we want to do at the interim, where we want to take some more time. We also want to relook at some of the charter. I don't think we need to be recharted, but there's goals that we had that we need to look into, and we will do that again in a September timeframe. Yeah, we've been hit pretty much by the COVID, and I think we're all a bit under the weather. Yeah, so I think without taking more time, because we're already are 3 minutes late, Dirk Trossen will present some work for actually related to routing and addressing. And I would like to mention that Tushar, who's going to have our last presentation, but not least, was also the Applied Networking Research Prize winner. And since that the last session, Dirk said that he was looking forward to start having maybe some work in in machine learning, intelligent networking, that type of stuff. And this is exactly what Tushar is going to present. And of course, the namespace is always a common thing between ICN and us. So I think those 3 presentations will be very complementary to what was presented before. So Dirk, please, we're waiting for your presentation.
Take the floor. Yeah.
Take the floor. Yes.
Slide sharing thingy.
Okay, what am I? For some reason, I'm not able to
Right, so you have to stop sharing first, Eve.
Yes, I'm trying, but my machine is giving me beeps. It's not.
Let me just do that for you.
Thank you. Perfect, thank you.
And Dirk, can you see share preloaded slides in the top, or is that just for shares?
No, I don't. I
Okay,
can see that I erased the slide request.
Oh, okay, yeah, right.
I think it has to go through you now.
Yeah, let me just bring your slides up and then I can drive them if you like.
Thank you.
Yep.
Yes, as Marie-José mentioned, this is work that's related to what you could call advanced packet forwarding, if you will, or routing. This is joint work with my Huawei colleagues, Karima, Ramin, Zora, and Artur, and also with George Carla at TUM, hence the two logos at the bottom. You can see, if you can go to the next slide, please. Oh, do I? Good. So the problem of random scheduling that we looked at, and there is an accompanying draft, wasn't the list that Marie-José looked before. So scheduling and joint network compute optimization has been talked about in contributions to COIN before. So the environment that we're talking about here is execution of services in a distributed service environment, where in particular virtualization drives the distribution of a service implementation in one or more service instances, right? They are available in one or possibly more network locations, and you have to make a choice which of the instances you would like to use for your computation. That's essentially the runtime scheduling problem. The additional problem comes in through, and we capture this through the notion of service transaction. It may require an affinity to service instance after you made an initial decision, because of ephemeral state that has been created. So this type of affinity needs to be observed. Otherwise, you're putting additional requirements on the application to move state, which you can do through shared data layers, but not all of the application frameworks necessarily work with shared data layers. So the problem that we outlined is to find the best service instance to serve the client transaction at runtime, while we also preserve the affinity after the decision has been made. And the solution is called computer-aware distributed scheduling. You can see the two key aspects. The one is it is computer-aware. So best that we put in quotes there is an awareness of the compute capability of the service instance. And it is distributed scheduling. It does not go via an inflection point. It's done at the ingress to the network. Okay, yeah, there is no. Thank you, Dirk, for giving me the control. I can see them. They're a little bit faded on some of the browsers, funny enough. Oh, was that correct? Yeah, that was correct. Sorry. So we're basing the cards idea on a system that routes service requests based on service identifiers. That's also, there's a certain proximity there to ICN, if you will, in the sense that so we have distributed, geographically distributed sites with the service instances. They are shown in red on the more right-hand side of the picture. Client issues service request, which is destined to a service identifier. And the incoming semantic router, which are the red bordered one, SR1, 2, and 3 for each of the clients, forward the service request towards a suitable destination, which is one of the possibly many service instances, the 5 that you can see here on the slide. That's 3 different locations. So you have 3 different locations, but 5 different instances. It performs an on-path forwarding decision, and that's the key part that we proposed, and that's compared to an existing DNS plus IP off-path decision that you could do as well. The affinity is ensured in the system by using IP locator for the subsequent request. So the service request is a special request as an identifier. It makes its way to, let's say, this instance, and then the subsequent requests for the transaction are using the IP locator of that instance to route the request directly to the instance. So only for the very first request, the decision is being made. What is computer-aware distributed scheduling? Now, one of the things we wanted to achieve is that we wouldn't need to signal permanently. A lot of work on computer-aware forwarding decisions that are also cited in the paper, but we wanted to avoid very, very frequent signaling. So we attached the computer awareness to something you can derive from the deployment of a service. So each service instance is assigned a normalized compute unit. This could be, depending on your orchestration framework, something like how many cores am I assigning to the service instance when I deploy this? How many threads, how many containers? The different ways and examples are given in the paper of how you could represent the compute unit. All the compute units are flattened and joined in an identifier specific routing identifier interval. You can see this on the right-hand side. So that in this case, it means, you have exactly one compute unit for the first one, you have 2 for the second one, again 1 for this one, 4, this is a rather big server at the bottom, and 2 again for the last instance. And it's then distributed to all routers correctly, the semantic routers, so not the routers, the standard IPv6 routers, only the routers at the inquest that are shown here. The scheduling now that you implement is a distributed round robin. So you essentially run through this interval in a round robin fashion. You have an incoming request and each of the identifiers exist at each of the inquests. So each inquest does, independent from the others, a decision of sending the first request to the first one, the next 2 requests to the second one, the fourth one to this one, etc., until it wraps around when it reaches the last one. That's what's being implemented. It can be implemented at link speed. We have a separate paper we published last year where we did a very similar mechanism in P4 and showed what are the issues with P4 in doing that successfully. So we implemented this in a simulation, and we also have now, by the way, a real implementation eBPF. But at the time when we published the paper, it was a simulation, and these results here are simulation results. The event-based simulator. We used 5 sites for servers, a service instance per server. You can also have multi-host, but we didn't do this in the simulation. The compute units are assigned at the start, so really emulating a deployment of these compute units, and the instances run for a certain amount of time until you may redeploy or reorchestrate your service setup. We have 5 inquest semantic routers as well. The service requests only go to one service function, and they're single packet requests with which they're sent. The main metric that we're interested in is the request completion time. So how can we improve the actual latency at the request level of these service requests? So scenario 1 we looked at was generally in scenario 1. And there's 1A and 1B, and B I will skip over in the interest of time. We had different design aspects. So what's the impact of the centralization versus the distribution? So we distributed the scheduling over a growing number of inquest points, and even in the end, into the clients themselves. Clients could be seen as an inquest point, very, very much close to the actual application, versus an idealized central scheduling. So idealized means we neglected the actual path latency to route to a central point and only centralized the actual logic. So not necessarily the actual latency. Obviously, you will have different latency. And the observation we got from the simulation is there's a natural effect of the distribution on the mean RCTs, which means the distribution itself, the fact that these schedulers run independent from each other, is not particularly large. When you start growing this to very many inquest points, then you see an increase in RCTs when the system load approaches 100%, but generally the impact is relatively small. So that was one of the aspects. So, and again, this obviously does not take into account the latency through running via a centralized point. If you take that into account, the numbers would get better again for the distributed scheduling, where you do not have this additional latency. I skipped this one. This was actually in the PPTX that I sent in the PowerPoint. It was actually hidden. You can look at it separately if you download the slides. We then compared with other network level solutions. So we wanted to compare CARD's performance against other distributed scheduling mechanisms that in the sense of both factoring compute capabilities in the scheduling decisions, so they needed to be compute aware, To perform scheduling at the ingress versus at sites. So we wanted to compare this design aspect of cards. And we also wanted to evaluate the impact of distributing compute units across sites and within sites. So if there are imbalances of distributions, compute units, what's the impact of that? We used two schedulers. One is a random scheduler. It's positioned at the ingress node. It is not compute aware at all. It performs random load balancing by selecting an instance uniformly at random and then just sends it to the actual network location. The second one is called Steam. That's an Infocom from Infocom paper in 2020. So it was 1 year before we started our work. One of the co-authors, Ramin, is also on this paper. This is positioned at the site ingress. It's not at the client ingress, it's at the site ingress. And the actual network ingress nodes forward the request to the sites uniformly at random, but then is therefore compute unaware at the network ingress, but at the site ingress, it is using load estimation to find the right compute instance within the site. So it's kind of like a mixture of compute unaware in the network, but compute aware at the site. What we found in the comparison, not surprising, is that card significantly reduces the RST, in particular in high load settings, because it is taking into account even the distribution to the sites, the compute units of the individual instances, which Steam doesn't do. Steam, on the other hand, has issues when the system load goes significantly up above 80%, as you can see on the right-hand side. It jumps quite significantly, even above the random scheduler. What we then looked was the imbalance of the compute unit distribution. So we created imbalances across sites. The normal configuration was roughly the same compute unit number per each of the sites, and then within the sites, roughly the service instances were almost the same distributed. And we changed this now in making one site very, very big and the other ones relatively weak in compute units. And equally, we had in the second sub-scenario, we create the same imbalance within the site. So one of the service instances was very big compared to the other service instances. And what we could see is that the Steam handles the contention quite well when there's an imbalance within the site, because it uses load balancing within a site. Hence, it can obviously deal with the imbalance, but it cannot deal with the imbalance across sites because it's compute unaware. CARD performs well across all of the scenarios because it is generally compute aware even across sites, and hence it outperforms all of the other ones. The random scheduler is particularly bad across the scenarios because it is simply unaware of the compute capabilities. If you have imbalances, it shows that quite badly. We also used the use case-driven analysis, and here we set the simulation parameters. This is kind of like a media scenario, since I mentioned media before in the Icnrg as a potential new work as well, where we have individual service requests, for instance, for content retrieval, or which could be either video or it could be software uploads, where I would like to have something, I'm getting a larger chunk back. So it's kind of like a rather ICN-ish scenario, if you will, right? And we compare this to existing long-lived approaches. And what we mean with long-lived approaches is an approach where a decision which server to be chosen is relatively long, and this can either be and we chose two, it's a 1 minute transaction. So after 1 minute, we essentially recalibrate. That would mean we issue, after flushing the DNS cache, we're issuing another DNS request, hopefully getting another choice now. And we used random as the comparison there. We also compared random choice at packet level, so where you would make a change even at the packet level. And what we can see is the performance of cards, even up to very, very high. The vertical line here is 100% system load, even when the system load approach is 100%. And what's more important, because of the use case-driven analysis, we set the latency, the inter-arrival time at 2 seconds. I said, well, what about if we have an upper bound latency of 1.5 seconds? So meaning I still have enough time to receive the packet and do whatever decoding I need to do, but 1.5 seconds should really be the upper bound latency. and what is the number of clients where this upper bound latency is being exceeded. And we can see that cards, in comparison to the other mechanisms, serve significantly more clients. So if you draw now a horizontal line, which would be very much at the bottom of this graph, you can see that cards serves 24,000 more clients than Steam, and 162% more, even more clients for the long-lived affinity scheduling. Sorry, for the packet level scheduling versus the long-lived affinity scheduling. So the packet level computer-aware decision, a little bit expected, has a significantly higher performance. So what's the conclusion? Well, the conclusion is that we try to show with this work that we can integrate computer awareness into the steering decision at the data plane level. These are two pieces of work, the system that we outlined in the paper, but also the accompanying P4 work that we've done before to show that you can implement this at the data plane level through programming frameworks like P4. The computer awareness here is a relatively static computer awareness, so it doesn't require frequent load signaling. It just says, well, are you going to put a big server versus a small server somewhere? That's already enough to make fairly good decisions, and it doesn't have much signaling overhead. That's the good thing. Significant performance improvements in the simulation, we've seen that, including also to serve more clients. So where do we want to push this work? This was, as I mentioned, IFIC networking paper, and my apologies for the mix-up was getting the proceedings. I accidentally disclosed the author link, as I was told later, and the website had to be shut down, so I went to the coin list. The link was only live for a couple of minutes. The proceedings should be available now, even though I don't have the link handy at the moment. What this did, it is a horizontal comparison. It compares cards with two other mechanisms at layer 3. What we've done as follow-up work already is to answer the question, what about if you use cards? So there's no particular reason why you use cards at L3, right? You could use cards at L7 as well, right? And that's a vertical comparison. And we did this at the moment in a new paper that we published in the upcoming FIRA workshop, where also the namespace paper that you will hear next is going to be presented, which compares what we then position as an off-path traffic steering at L3 against, an on-path traffic steering at L3 against an off-path indirection-based resolution at L7. And it compares, so that it allows us to somewhat compare the usage of the same mechanism, computer-aware mechanism, but with different systems at test. And you can find those results in that paper. I think the proceedings will be live at some point. The workshop is going to be in August, third week of August. That was it. Thank you very much. Any questions, reactions? Dirk, yes.
So I don't want to start a red hole discussion here, but why call this semantic routing? So what do the forwarders have to know about semantics? Isn't this just names that they need to know and then make the forwarding decisions based on that knowledge?
Yeah. So the semantic here is the service identifier. We actually changed the name in the FIRA paper, so you won't find semantic anymore. This paper, I think, was written initially actually for Infocom last year when we called it semantic router, and we called it after service router because it's a service identifier. So it's a bit more descriptive as to what the semantic is. For the same reasons, you weren't the first one that actually asked for you. Well, if it is a specific semantic, why do you just put the semantic into the name, into the description, which we did. I just use semantic router because that's what's written in the paper.
Okay, thank you.
Jeffrey.
Yeah, this is Marie. There's a question also from the chat, Dirk, which is from.
Oh, sorry, I didn't go there. Sorry.
So, what is the advantage of doing this at L3 versus 7? And we will put the paper that's is cited there in the minutes. So maybe you can answer to Ken.
Yeah, so I mean, this obviously goes after, at the paper that I didn't talk about, which is the one that comes in FIRA. We looked at this, and of course, the first thing you have the initial resolution latency, which is, you can quantify. And we do this actually in the paper. What's the typical initial resolution latency in DNS with optimization in DNS has significantly gone down. But the other one that we outlined in the paper is actually not necessarily an improvement of the average latency, but the variance of the latency. And this is quite clear. If you think about a problem when you, instead of distributing a smaller number of clients to a fixed server, you now have the option to pick among a larger number of clients more servers. So you have an MM1 system with n divided by k clients versus n clients in an MMK system. Queuing theory will already tell you average latency is about the same. It's the variance that is impacted. The variance significantly is reduced. So if you have use cases like which we have in the FireEye paper, like AR, VR, actually the reduction of the latency variance is a very, very good thing, right? What you also have is a scenario that we have in the FireEye workshop where about resilience. You share the damage. So we're overloading one of the servers. If you have been attached to the server in a longer lived affinity, obviously you're being affected immediately, and you will be affected for the duration of the outage. While in the L3 mechanism and the scheduling happening across the servers allows you to distribute the impact of that. It's not a failed server. We actually we increased the latency from that server. Is distributed across all of the clients, and hence you get overall better performance. Still good enough performance for everybody while nobody's really negatively affected. So these are some of the takeaways we have in this FireEye paper. But thanks for the reference. We certainly add this one as well. Look, are you still in queue or you're again in queue?
I just wanted to make sure that there was who else is in the queue. Yes, Dirk.
I would also say that in the interest of time, this should be the last question, or maybe we even take this question to the list so that we have time for the next couple of talks.
Yeah, happy to do that. And yes, Colin, thank you for finding the paper. Colin put the paper into the chat. When I checked it the last time, they weren't online yet. Thanks for pasting it.
Okay, I think Andy, to you. Thank you. That was easy. Dirk, you're driving the slides. Great.
I passed control to Andy, so he should be able to do it now.
Okay, this is all fairly new to me. Oh, and it's come up on the wrong camera as well. So you're getting a side view. I won't try and fix that. Yeah, this is some put together fairly recently. I don't know if maybe go on to the next slide.
I think you can do it yourself with your cursor keys.
Okay. Yes. Yeah, this is it's like a preview. We've had a paper accepted for the same SIGCOMM FireEye workshop that Dirk Trossen just mentioned. So this is like a preview of what's in that paper without necessarily getting into all its detail. It's also, and we've got that's the reference for the workshop. We think the agenda hasn't actually been fully published yet, but presumably will be very shortly. This has also come out of work within a European collaborative project under Celtic Next between UK and Germany. So there's one of the nice things about this is we've had a pretty broad range of input, including from automotive and video surveillance partners, which I'll come to in a couple of slides. With background is the question that we were asking ourselves was looking at some of the applications we've got. The general go-to solution that exists at the moment is microservices based architecture, normally based on one or other form of container modularization and hosting arrangements. And there's an awful lot of traction of that in the industry at the moment. And we started by noting that there's a lot of good reasons why the modularity associated with containers seems to be a good thing, covering quite a wide range of things. So starting even from the code development, if you're following the agile agenda and looking for a modularity, ability to refactor and so on, it provides a very good way, a good unit of modularity in your application development. It's a basic point of abstraction, service abstraction, by which the point at which you don't see inside to the implementation, again, which goes alongside some of the ability to refactor without impacting the wider system. It provides heterogeneity between development or different runtime environments, different language environments, and so on. It's also a point of integration and module test and end-to-end system test in CI/CD pipelines. It is our basic unit of distribution. And I think from our point of view here, it's also the primary point of interaction between the application and networking. So that's the way we'd encountered it at the moment. And certainly what we were taking is there's a lot of momentum to say this is a jolly good thing. All these things come together at one point. But it does still ask the question, does one size really work for all? And so we'd been identifying a number of issues where it's not immediately clear that this is the best long-term answer, or it can't be improved. So at the moment, a lot of the distribution is focused around distribution within a data center for some of these other aspects, not necessarily distribution as in physical distribution. And when we think about physical distribution, there are some more demanding constraints that present a great more complexity in working out the distribution and the management of the distribution. The scale of the service abstraction, the point of service abstraction, is largely fixed. So once you've decided your web services, for example, your web services interface, it's hard to go back and then break it open into subcomponents that are within it and say, I want to distribute a part that's within a container module, take that out and distribute it somewhere else, which then also sets up a trade-off that you have to decide fairly early on in the in your application development. If you choose small modules, that gives you a lot of flexibility, particularly in the way you might choose to implement the distribution. But you've now created a large number of networking interfaces between these small modules, which create a performance overhead. If you select large modules, you can greatly improve the efficiency of the communication by internalizing a lot of the communication within a module, but now it's inflexible and it's much harder to break open bits in the future. And then coupled with that, some of the solutions that are out there at the moment, sidecars and proxies, for some of the compute environments we've been looking at, would be very heavyweight indeed. So that's some of the background to the way we've been looking at this. The couple of use cases that have been really interesting, certainly I found them cause a lot of good thinking in understanding what drives the potential for physical distribution. There's been an awful lot of discussion about edge compute. One that we've been looking at, distributed video processing, does appear to really produce a use case where out at the edge processing of upstream video does make a lot of economic sense. If you've got a video application where you're wanting to extract features from the video in real time, if you try and do that at the camera, then that's quite heavyweight and costly addition to the camera. It also makes upgrading or changing any algorithms you're using much more complex, because you've got to get it right up to the camera, and there are all sorts of security issues associated with trying to upgrade the software on it. If you bring all the information up to the cloud, well, firstly, you require the full video bandwidth all the way up to the cloud. It's also got the potential issue that what you've uploaded is the full raw video stream with all sorts of other information which you don't necessarily want exposed and cross-correlated in a way that you never intended for the particular application. So the edge, doing the video processing at the edge would appear to give you the best of both. The other one, completely, in so many ways, completely different, is looking at the automated production facilities in a smart factory, where the sort of things that we understand are developing there is going for a greater scale of production automation, moving where you've got and changing from an environment where you've got a lot of legacy or existing interfaces for sensors and actuators, to have an architecture that's a lot more modular, where the compute facility may be in very small boards, where a Raspberry Pi may even appear fairly heavyweight, that is connected directly to the actuators and sensors, but is also doing a lot of the compute in a distributed way. And when you start looking at this, it looks like architecturally a very similar sort of architecture to some of the applications we've been looking at that are much more large-scale WAN type distribution. So that it seemed to us that there's a growing convergence between these, what are very, at the moment, very specialist, very small network environments and production facilities are becoming to look much more like the sorts of distributed applications that we might see in a wider network. Then coupled with that is one of the things that drives this is that as the production gets more complicated, the time to reprogram is a big concern, and the modularization of the compute potentially can help that very considerably. So the sort of basic architecture we've been looking at is represented here, and I won't particularly go into the detail. Key points are that at the moment there is almost complete isolation between application namespaces and network addressing, and we end up with these fairly heavyweight adjunct devices that, amongst other things, are essentially mapping the application namespace to network addressing, so the sidecars and the proxy load balancers and so on. So what we're looking at and what we've been, and what the paper comes to is, what ways can we improve the way the network works that can give a much greater visibility and connection between the namespaces of the application and network addressing. And so the three things that we've been looking at, and the three things that the paper concentrates on, firstly,
Can I just request, in the interest of leaving a little time for our last speaker, that you try to wrap up in the next minute? Thanks.
Okay. So the first one is bringing together the compiler and the orchestrator, which are the things the compiler maps the application namespace to addressing in the compute architecture. The orchestrator maps application things to, or the services to network addresses. If we could bring the two together, then the application could see much closer to the way the network addressing works. And this is one of the things that we've been that would potentially avoid the need for the sidecars and the proxies. There's a lot that we sort of look into this, and happy to sort of take further discussion on. The next one is that an efficient way of trying to bring this into a common framework is defining all the layering, whether layer 7, layer 4, layer 3, whatever, rather than by an intent of what should be, but actually looking at what a function executes on and what it's transparent to by an observation of what it does. That then gives a clear framework for both the application and for the network.
Can you please, we have another presentation and we promised the person full 15 minutes. So we really need to conclude now.
Okay, this is the very last point here. The final one is possibly most radical, is that in order to join up the network addressing much more coherently with the namespaces of applications, the network addressing would work much better if it started as fundamentally private addressing that then can be extensible and contextualizable in the same way that namespaces work. This would also facilitate security.
Okay, thank you. We really need to move on. We can move the discussion on this to the list. I see there's discussion on the chat. Maybe you want to have a look at that and respond, and we're going to put that in the minutes. Thank you very much. And Tushar, please, we're waiting for you. And Tushar is local, so this is wonderful.
Can you hear me?
Yes.
Is it possible to give control of the slides? I'm on the meeting.
Yeah, just trying to find you in the list. Just a moment. Oops. So I don't see you in the roster here. What's going on? Ah, here you are. Okay. Sorry. You have control.
Awesome. So, hi everyone. I'm Tushar Swami. So, I'm going to be talking about building adaptive networks with machine learning, and more generally, the role of machine learning in networking infrastructure. So, more and more, we're seeing like network complexity increase, and they can benefit from data-driven decisions rather than the many hand-tuned heuristics that we find in the network today. And so machine learning is a good solution here in the sense that we're essentially customizing our algorithms to the traffic and data that we're seeing in the network. So this isn't in and of itself a novel idea. There's been a bunch of papers published on anything from security, control, and analytics, different kinds of machine learning applications. But the issue that we found was that a lot of these are just running in something like TensorFlow or PyTorch, essentially in software, and that means that it's not really feasible to deploy them into a network because it's not clear how exactly they would fit into the network and where they would run. So that led to the first piece of our project, which was Taurus. And I'll go over this quickly because I talked about this on Monday, but the general idea is that we're going to take our software-defined network and we're going to slightly modify it where policy creation takes the place of not just flow rules, but also machine learning training. And then in the data plane, in addition to our typical packet forwarding with match action tables, we're also going to do decision making with machine learning inference. So the control plane will be developing new models based on information that's taken from the network, and it's going to be installing model weights into the data plane similar to flow rules. So the issue here was, if we're operating in the data plane, we need to be doing our ML inference fast to keep up with typical data plane operations. And so that led to Taurus, which was a switch architecture, a pipeline for enabling ML inference at a line rate, at a per packet level, and being able to essentially give you a programmable fabric so that you can put in different kinds of machine learning applications while still meeting your per packet line rate operation. And so we're reusing a lot of typical programmable switch hardware like packet parsers and match action tables, but now the packet parsing is doing things like feature extraction. We're using match action tables for rule-based pre and post processing. We have our typical traffic manager, but we've inserted this MapReduce unit, so based on the MapReduce abstraction, and that's what implements our machine learning inference. So the takeaway there was the robustness of our network is going to be based on the quality and speed of your reaction, and that means that machine learning inference should happen at a per packet level in the data plane, and this is what the Taurus architectures aims to do. So we published that in ASP+, but that brought up some follow-up issues. Namely, how do we program Taurus-like architecture? Because now what's happening is that we're asking network operators to be familiar with networking. They should be able to do all of the machine learning hyperparameter tuning and architecture search. And then they have to have some knowledge of the hardware itself in order to efficiently program their models. So it's actually kind of a lot to ask. And this was one thing we found by talking to different people in the networking community. They said if you give us an easier way to program this, an easier stack, we'd be more inclined to use it. And so that led to our next project, which was Homunculus, which was essentially a high-level compiler or framework for generating these data plane models depending on what kind of hardware you had available. So the idea was that the user gets these very high-level directives that they can use to essentially request their applications, and they can provide the different network and resource constraints that are available in this environment. And then the compiler will simply generate binaries for your different data planes, in this case, a Taurus switch with optimized ML models. So this is the general architecture of the Homunculus compiler. There's some more complicated stuff on the inside, but really it can be broken down on the left here into 3 core pieces, which are the front end, the optimization core, and then the back end. So the idea here is the user is inputting some sort of data set for their application. Let's say in the case of anomaly detection, maybe you're having the KDD intrusion detection data set constraints. So they're saying that my switch has this many resources, maybe some limitation on SRAM, on-chip SRAM, or DSPs, match action tables, and whatnot. And also network constraints, like I need to run at 1 gigapacket per second, or I have a latency requirement for my SLO objectives. Each switch needs to run in under 500 nanoseconds or something like that. So you input that data, it goes through the compiler, and then you get a binary for your data plane. So a little bit more concretely, you can imagine the users programming their switch in, say, P4, And then the machine learning portion is programmed by providing this data and configuration information. And then we're going to generate these ML models. And this is sort of the key here. We have so many different constraints between the network and the physical resources available that it makes it very difficult for a human to program it. But that means that it actually reduces the search space in an AutoML fashion to the point that we can actually reasonably traverse the AutoML space and come up with optimized models here. And so to do that, we actually use multi-objective Bayesian optimization with feasibility constraints generated from the network and hardware constraints. And so we're generating different ML models and testing their feasibility and using that to guide the AutoML search. And then we're generating whatever backend specific code you need for your switch. So in the case of a Torus switch, we program the machine learning portions in the spatial hardware description language. So that's what's being generated from the machine learning models. So just going through quickly a little bit more in depth on the different pieces here. At the front end, we call it Alchemy. It's really just a Python library. So this is the full code that you need for generating a simple model. In this case, we're doing anomaly detection. So you can see at the top there, you import your Alchemy library. In the second block here, you provide some user function for loading your data. In this case, we're just loading it from a CSV file, and it's under this data loader annotation that allows the compiler to wrap it and figure out what to do with it. You specify your model, some sort of optimization metric, and what kind of algorithm you want to use. You can actually even leave these blank and let the compiler choose. And then our constraints. So we have performance constraints. You can see throughput and latency here, and resource constraints. And this is all, these constraints are being placed on a Torus platform. And then finally, we ask it to generate the binary, or bit stream in this case. So moving to the optimization core, once the user has provided all of this information, we actually want to generate our models. So this is the piece where I mentioned earlier, we're doing Bayesian optimization using the hypermapper package, and the hypermapper is suggesting batches of hyperparameters. So this is everything from, say, the number of neurons and layers in the DNN, or the different unrolling factors on different layers in your DNN, and different parameters in the hardware that would allow it to be mapped more efficiently. So that will be sent to Homunculus, which is then going to start producing candidate models based on these hyperparameters. It's going to test the models and see how well they're performing, say how good or bad your accuracy is, and then doing these feasibility checks. So if someone requested 1 gigapacket per second throughput, did this model that I tried out actually meet that? Does this model map properly onto these resources? And so all that information is going to be sent back to Hypermapper, which is going to continue the Bayesian optimization process. And based on that information, it's going to refine its search more and more. So jumping quickly to the back end here. The back end is responsible for the actual code generation for your final switch hardware, but also doing these feasibility checks, like did I meet the throughput or did I run out of resources? And that's really just a built from a template library. So this is all supposed to be modular, so you can slot in different backends into Homunculus. But in this case, we're building a multi-class classifier with a DNN with packet parsing and deparsing. So we're just building out of these smaller component functions, and these will all be customized based on those hyperparameters that that were suggested by the Bayesian optimization process. So just some quick results here. We tested it with a baseline of 3 different applications versus our Homunculus version that was automatically generated. The baselines are hand tuned. And you can see in all of these cases, we're getting a higher F1 score. And this is without any human intervention. And the secret behind this is that the baseline applications are done abstractly they're just put into TensorFlow or PyTorch. Whereas in Homunculus, you're specifying the actual platform. So you can make better uses of the resources because you know what's available. So just to wrap this up here, Homunculus gives you a high-level interface. It makes use of the network and resource constraints and generates binaries for your models. So there's a link for the paper here. It's actually under submission, but there's an archive paper. So the final piece of this then is if we're looking to work on network infrastructure, how do we supply data to Homunculus? So now we have our Taurus data plane, which is doing line rate per packet machine learning inference. We have Homunculus on the far right there that's producing models for the data plane. And the last piece here is, and this is current ongoing work. So how do we take telemetry data and clean that data to feed it to Homunculus so that we had this loop of the network essentially taking measurements from its own data plane and then building progressively newer and better machine learning models, which then it installs back into the data plane and just keeping this loop going. So we have a simple pipeline here set up with a streaming database doing basic cleaning, data extraction and repair, augmentation transformation, and then some automatic labeling with different oracles. But really the takeaway here is completing this loop, which gives you this adaptive sort of feedback loop within your network, allowing it to modify itself for the different ML applications that you're working with. So that's it for me. I have links here for the Taurus and Homunculus papers, and we actually have an FPGA testbed for Taurus if people want to try out. And at SIGCOMM this August, we're giving a full day tutorial if people want to get their hands dirty. So I'm happy to take any questions.
Thank you very, very much. Yeah, this is the type of research that this group is absolutely interested in, not only because it has this idea of the computing in the network, but also the data-driven approaches and the idea that AI can be a tool in networking, not just some kind of magic that people think they put everywhere. I don't see any questions.
Oh, I have a question. Sorry, I'm jumping the queue.
Go ahead. Go ahead, Eve.
Okay, this is Eve Schuler. And I guess what this goes back to, so what I heard you say was that you're putting, the ML needs to be line rate, the feature extraction. And that seems to be sort of one of the challenges here is not just match action as we know it for packet headers, but there's this whole other kind of algorithmic stuff that has to happen at very high speed. What kinds of feature extraction? So you talked about, you said there were sort of 3 use cases that you applied this to, but I've been very curious for a long time. In this group, we've talked about something called ubiquitous witness, which is really taking image data and doing feature extraction. And have you done anything along those lines that would potentially have a larger overhead and kind of thwart you in this regard?
So we haven't done much with image data at the moment. So in this case, feature extraction is more based around like predefined headers. So say like our packet parsers and match action would be pulling out, say, like an IP address or something of those along those lines. But yeah, we're looking to start dealing with some sort of image classification networks in the data plane. But yeah, we're not certain actually what like the best use case here would be to motivate say grabbing images from your packet, and then how that applies to the network
So things
infrastructure.
further into the packet, right? Right.
But
Okay.
yeah, it's definitely an interesting thing. There is the somewhat of the downside that a convolutional neural networks that are used for image classification they tend to be very large, and we're still fairly resource limited on the switch. Even though we can do some data plane machine learning, the networks do have to on average be smaller than like the ResNets and those kind of like the CFAR10 networks that you see in like the typical ML competitions.
Thank you. That was a great talk.
Yeah, thank you very, very much. Other question? There's somebody at the mic.
Yeah, I have a question, Tushar.
Can you identify yourself, please?
I am Hisham al-Bakuri. So my question is, you update the model inline? Do you update the model inline in the data plane itself, or the model is created in the control plane automatically using these tools, but it gets updated also by the control plane, not in the data plane, right?
Right.
Okay, that's it.
Yeah.
Thank you.
Yeah. So the data plane is as far as the data plane is concerned, just has a static model. It's doing inference by applying it, and then the control plane is responsible for taking measurements in the network, refining models, and then in its own judgment, when it's time, sending those models out to the data plane.
Okay, well, I guess we're over time. So thank you. We're going to see you at the interim. And Tushar, please join our list and participate in our discussions, because your work is absolutely related to what we want this group to evolve into. Not just the original, using P4 to do match action, but what else we can do with all of this once we have a framework. I would like to thank Licia to have been our, well, for me, an avatar, but for you guys, a real person. Thank you very much, Licia, for having given your time for us, and hopefully it was good. I would like to thank also Dirk and Dave to have allowed us to be hosted in their 2 hour. We reorganized this a little bit at the last, a bit late, because we gave our own slot to somebody else who could not use their Thursday slot. And I would like to really thank ICNRG to have hosted us. I think we are showing more and more that there are so much in common between the two communities, so that I think it was good, and maybe we will have other similar co-located meetings. I was thinking this afternoon there's the distributed networking meeting, which also has a lot of overlap with what we do. And I think in terms of the research that was presented today, I think it shows that CoinRG is still very much a very active topic, and I think a more and more active topic in networking. And thank you very much, everyone. And for those of you who are local in Philadelphia, have a wonderful end of meeting. And for those of us who are a little bit under the weather somewhere else in the world, I wish us all to feel better. And for the other ones who are not sick, well, don't get sick, and please stay safe, everyone, and have a good flight back. And hopefully we'll be able to see you in London. Thank you.
Thanks for doing this with us, and thanks, Licia, for being our co-chair. Bye-bye.
Bye, thank you.
So the question, do I need to do anything, shutting anything down, or we just leave it? Okay, great.